Okay, we will start our session. If I can have your attention, sorry. So did anyone not succeed to create the output file from the past session? I'm seeing everyone was successful. So that's great. If just in case, if there is still someone that has still troubles to generate the data, we also created in the Thursday folder, we created the example data for you. So you could also work with those in case there was still any issue with creating the output files from the previous session. But otherwise, in the session that's to come, Francesco and I would like to walk you a bit through some multivariate data analysis. And so to introduce the topic a bit, I'd like you to imagine that you're in a tropical forest, and your task is that you have to sample 3 different plant species. So you're maybe sampling this big leaf down there, a palm and a banana species. And you want to ask how chemically similar are those 3 species. So would you then say that, let's imagine a hypothetical feature table where we have our plants and the compounds in the columns. So if you compare those plants, would you then say plant 2 and 3 are the most similar to each other because they both produce 3 chemical compounds, and plant 1 only produces 4 chemical compounds? Or would you say that plants 1 and 3 are actually most similar because they produce low amounts of compound 1 to 3 and high amounts of compounds 4 to 6? Or even a different scenario. Let's say you know the chemical structures of those compounds. Would you then say, okay, plant 1 and 2, they actually both produce flavonoids, and plant 3 produces terpenoids. So this is why we say plant 1 and 2 are most similar to each other. I think you can, on this very simple example, really quickly see that this gets more and more complex and even philosophical maybe. And even more so if we not work with just 6 compounds, but as thousands of compounds we have typically in our untargeted metabolomic studies. And so I think you would agree with me that omics data are oftentimes very overwhelming. We have a lot of data. And so we use multivariate statistics to find patterns. Just recapping very briefly about what are multivariate statistics. Basically, they are statistical methods used to analyze data with multiple response variables. Usually, there are more measured features or variables. So in our case, the mass spectral features or the metabolites, then we have samples. And the overall goal with those methods is that we look for a structure in the data. Then we can briefly classify 2 different kinds of multivariate statistical methods. We have methods which seek to discover a structure, and that's the unsupervised methods. So we have things like principal component analysis, principal coordinate analysis, PERMANOVA, or also cluster analysis and heat maps. And there's also methods which assume a given structure. Some example are PLSDA or random forest, but also there are many, many more. So what we are going to show you today is just a very, very small example of one very basic analysis you can do. But of course, there is much more that's out there. And also, we are just showing an example, so there might be many different ways to do things. I think There is not very much a standard yet in the metabolomics community. So I think the most important thing is whatever you do during, let's say, data cleanup, normalization, but also statistical analysis, is that you very accurately describe in your method section what you have done. So future researchers and yourself can refer to it as well. Yes, but just to give you a bit of background, I'm sure principal component analysis is a very common analysis that most of you are familiar with, but just to be everyone on the same page, I will give a short recap of this method and also principal coordinates analysis and PERMANOVA, and thereafter Francesco will talk a bit about cluster analysis and heat maps. What is principal components analysis in very few simple words? So basically, you can imagine you have maybe again your 3 plant species. You have the metabolomic profiles of those, and if you have just 3 species, you could imagine you look at maybe correlation of the compounds that you measure between species 1 and 2, and you would see there is inverse correlation. So that's one way to compare those 2 species. Then you could also look at species 1 and 3 and do the same, and then you would see that there is a positive correlation. So you could do this with an infinite number of times, but of course this is not very easy to see any patterns. So actually what principal components analysis does, it transforms those pairwise correlations into a 2D plot. So on this 2D plot, you will see that highly correlated samples they form clusters, and also that the axes in this plot are ranked. So if you compare species 1 and 3, and they have the same distance to species 1 and 2, then species 1 and 3 would be more different because the difference is more pronounced on the principal component axis 1. So this is about principal components analysis, but there is also principal coordinates analysis. So principal coordinates analysis is also called classical or metric multidimensional scaling. And what it does is it converts distances among samples into a 2D graph. So as compared to principal components analysis, we are not converting correlations into a 2D graph, but distances. And in fact, a principal coordinates analysis that uses the Euclidean distance is the exact same thing as a principal components analysis. So in general, we can basically speak about principal coordinate analysis just with different distance metrics. Just to showcase this again, so imagine you have your feature table with different abundances of different compounds in your plants. Then you would compare plant 1 and 2, and you would calculate the distance between plant 1 and 2, then between plant 1 and 3, and so on. And what you get out of this comparison is what we call a distance matrix. So you have on the diagonal, it's filled with zeros because obviously the distance between the same plants is 0. And then it's a symmetric matrix filled with the values of the distances between the respective plant species or any sample types you have. And this is then used as input to create your 2D coordinates plots, your principal coordinates analysis. But so there is, in fact, many different ways to calculate those distances. So a lot of different formulas. And the question is then, of course, are we using the appropriate distance metrics in the metabolomics field? And so this is still a very active discussion in the field right now. There is not really a consensus about it. So many different distance metrics are commonly used. I think one important thing to highlight is that all of them, they show you some truth about your data. So it's just different angles how you can look at your data. And so like finding the appropriate distance metric for your data set is really part of the art of data science. In the metabolomics field, typically people use the Euclidean, the Canberra, Bray-Curtis, or also the Jacquard distances. And the selection depends very much on the nature of your data and also the assumptions this distance metric makes. Some in more recent years, chemically informed distance metrics have been developed. We don't have time to go into detail into that, but I'm linking below to some references that you can read up in the literature. But basically the idea is that in addition to calculating the distances, you also consider how chemically similar those features are, be it by a network or by a tree structure, yeah, and so on. Then, so the principal components analysis is not dealing very well with many zeros. So that's why a lot of people like to impute the data. So that's what you also did in the previous step with Abser and Daniel. So in that case, it's suggested that you use other distance metrics or that, yeah, you impute. And also, so the metabolomics field is in many ways, the data structure is comparable to the microbiome field. So also there we observe that the Canberra distance is usually quite good in detecting patterns. But this is very empirical. There is no like systematic testing of that. And then also there is a metric, the Jacquard metric, that you can use if you're only looking at binary differences. So if you look at the presence and absence of your metabolites instead of the relative abundance in different samples that you measured. Yes, so this is basically how your principal coordinate plots would look like. But so this is just a visual representation of your data, right? So how do you know if this is also statistically significant? So if you have a control and diseased or some different groups, you want to distinguish how would you assess the statistical significance. And this is where the PERMANOVA analysis comes into place. So PERMANOVA is the permutational multivariate analysis of variance. And basically it tests whether two or more groups of objects are significantly different based on a categorical factor. So it's very similar to ANOVA, but it operates on a distance matrix that we saw before, that's created when creating a principal coordinates analysis. And this allows then for multivariate analysis. So if you have a hypothetical principal coordinates plot here, the PERMANOVA would tell you, it would give you a p-value. So here the p-value is 0.025, so that's a significant p-value. So that means there is a significant difference in the metabolomic profiles of those different sample types that we are measuring in this example, like bacteria, corals, food, and so on. You also get a R-squared value. This R-squared value you can interpret as the variation that is explained by this metadata group. So there, you could say that 35% of the variation in the data can be explained by different sample types. Yes, so that's and so what you would conclude is that there is a significant difference between metabolomic profiles of different sample types. And so as Daniel already showed you in some of the previous sessions, you can actually also view an interactive chime and pair plot from within GNPS. So that's a very handy tool if you want just to quickly explore your data. But you can, of course, also do your own analysis with your own code. And we provided you with a little example code on GitHub that we can now walk you through with your own DOME data set that you produced. So let's do that. So again, if you go on the GitHub page and you open the notebooks in Google Colab, and then the notebook you will select for this session is Notebooks DOME Stats and PCoA PERMANOVA Summer School. So you will open it again, and such as in the previous session, it's very important that you create a copy in your drive of that one. Okay, so now the copy is created, and I will just close the original file. And in my case, I don't have any data uploaded. You already should have the output files if you didn't close the session, but otherwise you can just upload your output files again. And so the file you will have to upload this time is the file that's called imputed quants table filled with, and then you have probably a specific value, so that might be different from ours here, and then with the cutoff used. So that's the one you created in the previous session. So you will upload this basically just by drag and drop to your Google Colab space. And also, again, you will upload your original metadata file. So the metadata you got from Massive. Here we are working with Lab 15, and you just drag and drop this over here as well. Everyone got that step? Anyone that needs help? You can raise your hand if you need help, and Francesco and Philip can come to you to help you. There is Anyone still needs help, or things are getting solved? Yes.
The name is not exactly what it is. Okay, or when we have
No, the file name doesn't matter. As long as it needs to be the imputed data table, as long as that's the case, it's fine. Yep.
So this is just
it's taking bubbles.
Okay, I think because of time, we will continue. I hope more or less everyone got something, but else just keep raising your hand and Francesca and Philip can go around. So again, we will install the libraries. This might take a while, so you can just start executing the code from the top. Okay, so we have that installed, and then you just call the libraries. And here we introduce the system time command. That's just to show for the next person that's opening the notebook when we have last updated it. So it just shows you the time. And so the only thing you need to modify here is basically those two first lines where you load the feature table URLs and the metadata URLs. So this whole string here, you will basically replace by your own feature table, which you just uploaded here. So to do that, you hover over your imputed quant table and you select copy path. And then you paste that path in here like that. And so you do the same for the metadata. You go to the three dots on the right, you select copy path and you paste it in here. And then you can basically just start executing the notebook one by one. I will walk you through it line by line just to explain what each line does. but you feel free to also experiment yourself later on. So here, as in the previous notebooks, we are just loading the feature tables. You get some dimensions of both. And with the head function, you can inspect how they look. So you have the exact same format here again, features in rows and samples in columns, and then the metadata with the sample names and different metadata or attributes in columns. Then we just execute some code to bring the metadata and the feature table in the same order and making sure that they have the same file names. So we can see here that one of the file names in the metadata is not in our feature table, but that's okay because that's the blank sample. So we don't care about that. So in the next lines, we just remove that file from the metadata. And we do some restructuring of the feature table, but you don't need to worry too much about those steps. Just keep executing them. And then we need to make sure that the feature table and the metadata table all have the same name so that we don't mess up anything with the stats analysis later on. And so this first line is okay if it says false, but the second statement should be true. So it means that your row names of the feature table are exactly the same as your row names in the metadata. Yeah, is it a question? Yes. Yes, it's also okay if both is true. Yeah, absolutely. The important is that the last one is true. And so you might have noticed that we used the imputed quant table and not the normalized quant table. You will see that different labs do analysis in different ways, and that's okay. There is many different ways to do data analysis. In our lab, we commonly do normalization based on the statistical methods we use. So here we didn't choose to do TIC normalization, but we are just scaling the feature table in both ways. And that is because often we have these very extreme values, so we would like to have them a bit more condensed. So we scale both in rows and in columns. But another option, of course, is if you want to work with the normalized data, you could also start with the TIC normalized data. And so basically here, after all doing some scaling and cleaning up our feature table, we are starting to actually do the multivariate analysis. So as a first step, we are calculating the distances, as you remember from the slide, between each of the samples. And the method we use here is Euclidean. So in that case, the plot, the 2D plot we will get afterwards corresponds to a principal components analysis that many of you will probably be very familiar with. And then we just do some exploration of our metadata to know what kind of metadata we have. So we have the different concentrations. We have only samples here, so no blanks left. That's what we want. And we also have the different concentrations in like two different data formats, in a categorical one where there's a letter before and in a more numeric way. And so in the next code package, you will use the distance matrix as input to create your principal coordinates analysis plot. This is what all those lines will do. And we can inspect this object. So we have here our samples, and then the position in principal coordinates 1 and principal coordinates 2, respectively. And then just to make sure again that our metadata corresponds to our features, that it's in the same order, we just do a quick check again. So this should retrieve true here again. And then using the ggplot library, we can then plot our PCoA plot, or here the principal components plot. And we can observe some trends in the data. So we have here the M samples, so that's the dome samples. They cluster up here, and we can see they separate from all the other concentrations. So each concentration group basically forms their own cluster. So what we can already see here is there is probably a difference between those different concentrations of algae, but it's just a visual inspection. So let's do a PERMANOVA to test if this difference is significant. For that purpose, we are using the Adonis 2 function from the vegan package. And basically what it will retrieve is, as I showed before, a p-value, and then an F statistic and also an R-squared value. So here it tells you basically that 75% of the variation in our data can be explained by those different algae concentration, and this difference is significant. So this was just like step by step how you can execute line by line, but maybe you want to change some parameters, and so it's not so practical if you have to change each line one by one and then rerun the notebook. So in order to make it a bit easier, we created a function for you, and this function, which you just load here, you don't need to worry much about what it contains, but basically what it will do is you just give it as input a feature table and a metadata, and then you define which distance metric you would like to use, and also which metadata column you would like to look at. And what it will do for you is it will automatically plot your principal coordinates plot for you, and also it will give you in the title the PERMANOVA results automatically, so the p-value as well as the Adonis R-squared. And so in that way you can easily change some parameters. So for example, if you don't want to look at those different concentrations in a categorical sense with those different colors, if you want to have a gradient like showing the least concentrated to the highest concentrated, we could change here the category or the metadata column used to a time point column. And then we see here that the most concentrated sample clusters up here, and then there is sort of a gradient for the remaining algal concentrations. Also, we could decide, actually, we don't want to impute any values, but we want to keep our NA values or our zeros. So you could do this with the following lines. Here we are just assessing how much percentage of our feature table contains zero values or NA values. And in our case, this is just 7%. So that's actually not high at all. There is many metabolomics data sets we typically work on that contain up to 50% of missing values. So probably there was, it has to do with how also you pre-process your samples, probably filtered out a lot of those very sparse data.
This is not using the computer control.
Sorry?
This is not using the computer control.
Exactly, yes, that's just the gap fill. So another factor is that we gap filled right during MZ-MINE pre-processing. So that gets rid of some zero values already as well. But I'm just removing the minimum value we imputed before and then replacing it with NA. So I have the original feature table back without the imputation. And then maybe we want to try a different distance metric. We don't want to do a principal components analysis because now we have our NAs or zero values in again. So we could use the Canberra metric. And again, we can observe the clustering. You can see it's a bit, visually it's a bit different, but the overall trend is the same. So we see there's a significant difference between those different concentrations. and the variation that it's explained by it, that varies a bit depending on what distance metric you use. So here you have 80% explained by those concentration categories, while before with the Euclidean distance you had 75% explained by it. Another thing you could decide to do is that you want to do just a binary comparison. So you want just to see, is there a difference in metabolites that are present or absent in each of the concentration types. So for that purpose here in this code line, I'm just replacing all of the NA values by 0. And then I'm using the card metric, the binary metric, to again plot my principal coordinates plot. And you can see here the difference is even more drastic, it seems, and 92% of the variation can now be explained by these different concentration groups. So one way I think one could interpret that is that there is not only a quantitative difference between those different dome samples, but there is in fact a qualitative difference. So which makes sense, I guess, if the more algae you have in your sample, the more different compounds also will be produced. So you can look at this both using the categorical coloring or the continuous coloring, whatever highlights the trend you want to show in your data. And then last but not least, you can also create a plot in a PDF format. That's the last line here. And this plot will basically be saved in wherever the output is going, you have set it. And so this is something you will use tomorrow when you look at how to create nice figures. So once you have created this output and selected a plot that you most liked, or you can also export several ones, you can again download this file and then save that one to your folder where you can access it tomorrow to do the more visual inspections and working with figures in different programs. Are there any questions right now, or anyone needs help with specific steps?
One question.
Yes.
There's more than one question. I'm there where you are.
Yes. Yes.
How would you like to look at these figures, or would you decide which one is best for your data?
I think it depends very much on the message you want to convey. Maybe your message is that there is a qualitative difference between samples that contain algae and samples that don't contain algae. Then I would use the binary metric, the Jacquard metric, because it shows a really large difference between the different groups. And also it's a binary metric, so it means that there is a qualitative difference. If you're more interested maybe to highlight the gradient, like from very high concentrated to very low concentrated, maybe a plot, something like this is more of interest, because you can see here the highest concentrated sample is clustering over here, and then you have more of a gradient with the remaining samples on the left. So it depends really, I would say, what message you want to convey. I would say probably, I haven't tested, but probably the results are very similar. They will not be identical, but the overall trend should be the same. Yes?
The export file you have, like how many figures are included? Just the one?
Yes, so I just, as an example, I just said like select one figure that you like most, that you want to work further with. Okay. But of course, if you want to export more, you could just copy this code block and add a new code, paste it. And then here you can edit. Maybe you want to use the Canberra distance instead of the binary one. And you want to use a different metadata category. So you want to use a sample. Then you place it in both instances. And now this will be categorical. And you have to give it a different name. So you say this is Canberra. And then you can just execute again. And you should have a new PCoA plot here, in theory. Yeah, there it is. Yes, so here you can sort of see a gradient of colors, right? So the purpose of the project Daniel worked on is that by preparing different concentrations of algae in the dome samples, you simulate the algal bloom. So maybe if Daniel, correct me if I'm not interpreting correctly, but maybe in an environmental laboratory, you want to observe this algal bloom. So you could then argue that you can differentiate different concentrations of algae in your samples, so you can locate them on the PCoA spot. So basically you could make predictions. If I get an unknown sample, where does it fit in on the PCoA plot? So it maybe fits in with the super highly concentrated, then you would say probably there is a lot of algae in there. That's just an example. I guess there's many other ways to look at the data. Yes, do you have a for the report? That's your choice, basically. So we just want you to explore your data. So whatever you find interesting to show, that's the plot you will show. Right, Daniel?
Yeah. I mean, showing sample to sample distance is probably the obvious one, right? Now, what like particular metric you choose? I'm able to test an orbit handling percentage and then check out if it's significant, right? So like that connection of like a PCoA to PERMANOVA, that I guess in that case makes a lot of sense. I would hope that all of them would.
They should, I guess.
They need a bit of time to digest.
Yes, I think we agree now. Yeah.
Yep.
Maybe with the at the beginning of the univariate thing.
Okay, so you would do
I would do it after lunch.
after lunch, before the lecture.
Yeah.
Cool. All right, then let's take a break and let's continue at 1:30.
If you still have questions.